So this video is for my Math 130 students, intermediate algebra, who are dealing with problems on continuous compound growth. This video is for Gabby and for Jessica, who asked about two different types of problems. This problem here is about bacteria. The number of bacteria in a certain population increases according to a continuous exponential growth model. So notice the word continuous exponential growth. So that's going to tell me that I'm going to need to use the formula A is equal to PE to the RT. That's our continuous compounding formula. Okay, with the growth rate parameter of 7.8% per hour, how many hours does it take for the size of the sample to double? All right, so to do this problem, the first thing we do is identify the formula that we need to use. Now the growth rate is 7.8% per hour. So that means R, which is the rate, is 7.8% per hour, but we need to change this to a decimal so we get 0.078. Always change it to a decimal. All right, so the question is they are asking us how many hours does it take? So in other words, what is the time? So find time. Find time t. So we need to find t in this problem. So we have the r, so we need to know what a and p are, and we are assuming that a and p is given in this question, but it's not given explicitly. Instead, it says, how many hours does it take for the size of the sample to double, double? So P means the initial amount, or it stands for the principal amount, how much you first started off with, and A stands for the finalized amount after the period of time, after time t. So if it says that how many hours does it take for the size of the sample to double, so we're going to start off with some amount for P, and then in A we're going to double that. So they don't give us the explicit amount, so we're just going to make up a number. So principal, I'm just going to say the easiest number to pick is 1. If principal is 1 and A is the finalized amount after time t, we know that A is going to be double of P, so therefore 1 times 2 is 2. So of course you could have picked 100 and changed this to 200. You could have put 50 and put this 100. So any number you put here, just double it right here. So here when I plug it into the formula, I get A is 2 is equal to P is 1, e to the 0.078t, right? So 2 is equal to 1. So I could get rid of this 1, so I end up getting e 0.078t. Okay, notice that my variable is in the exponent. And what we learned in this module is that whenever you have a variable in the exponent, you could log or natural log both sides to pull the variable in the front. So since the base is e, I'm going to natural log both sides. So when I natural log both sides, I can now use the property where the power, the exponent up here, could be pulled out in front. So reminder, this is the rule that if you have natural log a to the m power, for example, you could pull that m into the front and you'll get m times natural log a. That's one of the properties of logs, and that's why it's so powerful to natural log something, because the exponent can be pulled out in the front. Sorry, it's getting kind of dark here. I get natural log 2 is equal to 0.078 t times natural log e. So I pulled that to the front. So now my variable is sitting outside and it's no longer in the exponent, so we're all good in the hood. Natural log e is just simply 1. So I solve for t. To solve for t, I divide by 0.078 on both sides. So when I divide by 0.078, I end up getting t is natural log 2 over 0.078. That's the exact answer, but they want us to round this to the nearest hundredth, meaning round it to 2 decimal places. So when I round it, I plug this into my calculator. Make sure you know how to plug this in. You end up getting approximately 8.89 hours. Let me know if you have any questions on that. The second question I'm going to do is from Jessica, who emailed me this, or Facebook messaged me this problem here. This is about bacteria. Suppose that the number of bacteria in a certain population increases according to continuous exponential growth model. So again, the word continuous exponential growth. So you know you're going to use this formula here. A sample of 2,200 bacteria selected from this population. So this is going to be your P. That's what you initially start with, the principal amount. Selected from this population reaches the size of 2446. So this is going to be A. This is your finalized amount after the time period in 3 hours. So 3 is going to be time. Do not round any intermediate computations and round your percentage to the nearest hundredth. So here, Jessica already started the work, so she did it correctly. So she starts off with the formula. She identifies what A, P, and T are. She does it correctly. She plugs it in. So that is correct. She plugs it in. She noticed the variable is in the exponent, so she natural logs both sides. So when she natural logs both sides, she also divided the 2200 over here. So 2446 divided by 2200. So she divided it over. She natural logged both sides, and then she pulled out the 3R into the front, which is correct right here. So her question for me is, how do you solve for R? Well, the answer is this. To solve for R, you're going to divide both sides by 3. So my answer is going to be natural log 2446 over 2200. So I'm going to natural log this whole thing, divided by 3 is equal to R. So that was your main question, Jessica. You had asked me, what do you do with a 3? You divide it. So in terms of plugging this into the calculator, I'm going to get natural log. So there's a parentheses, 2446 divided by 2200. I close the parentheses, I press equal, can you guys see that? And then I divide by 3. And I end up getting 0.04. So the rate is equal to 0.04, it's 0.03533 on and on. But since the rate is going to be a percentage, we want to move the decimal twice to the right. So when I move it twice to the right, I get 3.53% is going to be the rate. All right, hope that answers your questions, you guys, and good luck on your finals.